Thank you guys for coming. How many of you guys here have heard about Cartesi before? You guys don't count. Okay, so I guess I have a good task ahead of me, introducing you guys to the next generation dApps. So what I mean by that is what you get when you can construct using RISCV, when you can get Linux as your VM to construct your applications. Things change when you go there. But in order to introduce what it means practically to you, I need to show you some examples so you can grasp the potential of this. So a little while back, about a year ago, somebody went to Twitter and asked about, like, if Ethereum is the world computer, why haven't we seen Doom running on it? It's a joke, right? But our friend did take this joke as a challenge, and he started running Doom inside the Cartesi machine and proving that you can actually verify on Ethereum. Not only that, but he's so passionate about games, so he was not just a challenging-seeking developer. He's actually passionate about games, so he actually took it to the next step and created Rives. So if you access Rives.io right now, or if you go to our booth outside, you can actually see these cottages in the style of 80s and 90s game being verifiable, run on Ethereum right now through the potential of the technology of Cartesi. And if you're really interested into that, you can actually develop your own cottages using the playground they created on their website. It's super easy to get started, and it really displays the potential of what Cartesi can do. Also, we have Bubble Wars. This is the most degenerate game I've seen in a while. It's one of those games where you have your character, and it gets bigger and bigger by eating smaller characters. There's a bunch of versions of this. But the size of your bubble is actually an ETH deposit. And in order to move, you need to create smaller bubbles in the opposite direction that you want to move by dispensing ETH. So you need to be strategic about it. And once you eat somebody else's bubble, you actually got all of their ETH. It's real, man. It's very degenerate. You should check it out. Another one that is really interesting example is Cryptopolis. One of our friends in an experiment week inside Cartesi created this SimCity game. So he took the original game of SimCity, the version that was rewritten in C++, and basically just ported it to the blockchain that easy. He just needed to compile it again for RISC-V. So he created a bit of a logic around it so it makes sense for blockchain. But as you can see, you can actually play this game and verify your actions on chain instead of actually having servers, centralized servers on the outside. Okay, so if you are interested in these projects and other projects, you can actually check rollup.io. You can see a bunch of other types of projects. Here, I brought the games, but you can see DeFi, you can see IoT kind of projects there. And that's it for an introduction. That's it for getting your mindset for what we are going to be talking about here. So I inspired you guys a little bit, I hope. I'm going to take you over a small overview of how Cartesi rollups work. The perspective of tooling and building with Cartesi, and architecture and closing suggestions. Sorry about that. But before I do it, I have one more thing to talk about. Apparently, somebody said that to grow Web3, we need to step on the giant shoulders of Web2. I don't know who it is, but I guess it was me. Sorry, guys. Now we can actually go to the overview. So, as Cartesi strive to bring a solution that can impact blockchain, we felt like we needed to explain in a much simpler way. And that is the merge of everything that the Ethereum experiment taught us about security and decentralization, but also the addition of this abstraction layer brought by RISC-V and Linux. And what you get is something that can be somewhat explained in this picture here. One part, you can get the expressive, general expressiveness of the execution environment. And in the other side, you can get a system that can be deployed in multiple different ways, as a sovereign rollup, as an L2, as an L3. And it can actually pick it apart and put it together with other projects and create things that we haven't thought of yet. So what it means when you're building with Cartesi, right? So in order to make this make sense to you guys, I need to make some small comparisons first. First one is the development side of it. So whenever you're developing with EVM, I have been developing since 2016. Lots improved, but I still feel like I have a plier, and I've been using it as a hammer, as a screwdriver, as a plier, as a cutter, and it's kind of nice, but it's very limited. But that is because we abandoned the full tool set that we had as a Web 2 developer. We had a bunch of cool things that help our daily work into expressing the business logic, our creativity, into higher level languages, into reusing each other's code. And this is well expressed through the building system. So when you're deploying a dApp using Solidity and equivalents, at some point you basically compile and you send that to some chain, and that's your deployment process, right? At Cartesi, your deployment process starts as a Docker build. So we created a way that it's more easy for people to understand through Docker to express what you need to package inside your Cartesi machine emulator to make your application work. So through a simple Docker file, you can express what is necessary for your application that can be infinitely sophisticated and complex to be an actual dApp, to be an actual smart contract that later can be deployed as a rollup. Now, I'm talking about Docker here, but how is it possible, right? That's the second comparison I have to draw. So being very lenient with Ethereum here, if you take the max block size, you'd have 30 million gas. That's not the ideal, but that's the theoretical limit. Then the cheapest useful opcode that you can have on Ethereum right now is either add or subtract. And this costs 3 gas. Effectively, you cannot create an application that only does addition. But supposing that we could, that would be a theoretical limit of 10 million instructions per block. Okay, so check this out. If you try to boot Linux right now, and we have the instrumentalization to see that, you'd see that it takes about 3.6 million cycles, CPU cycles, to boot Linux. Of course, I'm not advocating for us to boot Linux on top of EVM, but at the same time, I'm saying that if we need to go to the next stage, we need Linux to make it happen. So it's not going to be through EVM that we're going to do it. And since I'm still drawing the comparison, if we take the average blocks time for EVM, which used to range between 10 and 13 seconds, in these 13 seconds, in a small laptop, you could run 3.6 billion CPU cycles inside a Cartesi emulator. I know it's difficult to understand the magnitude of the difference here, so that's why we draw this picture. That black dot over there is how much computation you could have in an Ethereum block. And at the same time, you could have this whole graphic here as computation inside the Cartesi emulator. So that's what allows us to have this higher level of abstraction by being an application-specific rollup, but at the same time having this emulator that is much more expressive. Okay, now onto the rollups itself. I feel like it becomes a little bit abstract by the time I'm explaining this to people. So we have like this architecture picture to show a little bit how it's not that different from the other systems when we look from top down. So you're still gonna have your front end user interactions, sending transactions to some layer 1. Let's say you're using Cartesi as a layer 2. There, you're gonna have some smart contracts dedicated for the logic of validating things for Cartesi, doing the dispute resolution, grabbing the transactions, and turning them into inputs to your machine. Now, in this image, we chose to break it as Cartesi rollups being these nodes here, they're gonna be running, and whatever you send as smart contracts to the base layer, right? So actually, technically, the Cartesi machine is in here, But we break it down so you can see from the outside what's going to be happening with the Cartesi machine as you code your application. So you can have a bunch of different logic written in Python, written in JavaScript, whatever you chose, and also frameworks that as you host this, you can compile using the Docker build I just mentioned and build this image for the Cartesi machine here. Now, eventually, it becomes so much like a backend that we stop calling it really a smart contract and start calling it as a backend logic here, even though it still communicates through the blockchain. Okay, eventually, you'd have some kind of output that you need to effect change onto the base layer. And these can be feedbacked to the front end through the APIs that the node can provide, but also the changes that are affected on the base layer. It looks a bit abstract, but if you really think about it, it's still the same thing that you would see with an Ethereum network. You have some nodes, you have the interactions through the RPC with such nodes, and you have the logic that goes through them. Okay. So I know it looks too abstract still. For this instance, I have a very small example. I won't go over something so complex because we don't have a lot of time. But here I have a very basic echo application. So whatever you send to it, it replies back the same thing. Oh, sorry. Over there, you're going to see one of the CLIs that we have to help you bootstrap your application. This is basically a CLI that sends transactions to the base layer. In this case, we are using Envo as part of the developer environment. And here is a theoretical call that you can do for one of the graphical APIs that the node provides you to see what was produced and eventually can be sent back to the chain. So on the right side is the important thing. I don't know, is it difficult for you guys in the back to see the code? Is okay? Okay. So you can start by noticing that this is very simple Python application. There is nothing too special about it, which just goes to show how this is so similar to the desktop environment that you have. Now, up there, you're gonna import things normally. And here you have this roll-up service that we embed into your system to facilitate the communication in and out of the blockchain. So through this API, you have a very basic gateway of abstraction to handle your application itself. Now you have two main sections here that are very important. First one is the running mode of the machine itself. So for whoever is already used to blockchain, then you know that the VMs can be in read mode or write mode, right? So whenever you're doing EVM call or you're actually sending transactions, this can be abstracted away by the API through this advanced state or inspect state. So as you get the request, you're gonna notice that you can check the type and see whether or not your machine is in read mode or write mode. That's very important as you develop. And the second thing that is just as important is your inception, which is this finish endpoint here. So you can think of it as you build the application, the very first time that you go through this code here is like your construction call, and then the machine goes to sleep. And then the very first time you get an input, the machine wakes up exactly at the line 24, and now time has changed. So from here, you can see this is an infinite loop. This is one of the ways that we thought that is comfortable for developers to abstract away any custom logic that would be attached to this or that other language, to this or that other framework. Just by building a simple loop, you can attach anything else from it. Now, as you can see, we're gonna get the roll-up request from this as it resolves. We know this is gonna be a transaction because of the way I send the message. So here's gonna be advanced state, and now we're gonna go for the handler. Here's a very high-level handler. You can create as a drill-down version as you want, a very granular version of handling functions here. But as a top level, you can see that there, we only created a notice, which is one of the 3 types of output the Cartesi machine can provide you. I won't get too much into detail, but you can think about it as an Ethereum event. coming out of the rollup itself. But it's a provable event. So as you see, you get the data. The data is inside this payload key here. We can just create a new notice with the same payload. And as you query the API, you'd see the payload over there being the same. So it's a very simple life cycle that allows you to do very sophisticated application later. Okay, so before I open for questions, I'd like to invite you guys to also check out this Udemy course that goes more in depth. That's about 1.5 hours course, free course to understand Cartesi development. But also tell you guys that there is a bounty for whoever completes the course. So there is a $20 bounty for people interested in engaging with the content. Then I'd like to remind you guys that we have a running challenge called Honeypot dApp, which is a dApp where the foundation deposits in fixed time intervals more and more money there, more and more CTSI tokens, to incentivize people to check the infrastructure, check the code, check that things are secure, and if they find any flaw that they would allow them to steal the money, they are invited to. So far we've been accumulating 760K for a while. Nobody has done it. I invite you guys to join our community, and I'm open for questions.
But first, let's have a round of applause for Gabriel.
Thank you.
So what you're saying is you're using a Linux-based VM for your dApps, right?
Yes.
What would be the advantage of that compared to any other alt VM?
You don't need to figure out how they build their system. You don't need to adapt all the libraries that is available out there.
Okay. The shorter the answer, the better.
Yeah.
And what are your plans for the future? Anything cool coming up?
There's a bunch of cool dApps. That's what excites me a little bit, like what people have been building with this.
Mm-hmm.
But people are invited to check the website. There is the technical evolution plan to see what technically we're going to change into the system and improve.
All right. Sounds like too much to talk about right now. So
Yeah.
come find Gabriel somewhere around this venue.
Yeah, we are
This afternoon.
just the first booth over there.
You what?
We are just the first booth over there.
Oh,
Yeah.
the first booth. Yeah.
Yeah.
Just the first booth in the hallway. Any other questions from the audience?
Yes.
I'll go there. Just a sec.
Hi, you show the Python code, and if you assume that it will be run in blockchain, what will happen if I do one little trick? I will do import random and calculate some random number.
Yes, that's funny, right? So the first thing that we did to create the emulator is to remove any source of entropy. So while the function is called random, it's actually pseudo-random, right? And because the system itself has no entropy, every time you run the transaction again, it's going to give you the exact same number. So you can be tricky about it, funny. You can actually do like prankster kind of thing, but it's going to be transparent to everybody. Make sense?
What about the real numbers and multiplication and division is the real number?
You can think of it like as there is no float numbers inside the Cartesi machine. There is an instruction to deal with it, but down to the core of it is actually integer operations.
All right. Another round of applause for Gabriel.
Thank you, guys.